7.4 Relative Rates of Growth. The outline of this video is as follows. We will begin by developing an intuition for the relative growth rates of functions, exploring why some functions, like exponentials, grow much faster than others as their input becomes very large. From there, I will introduce the formal mathematical definitions that allow us to make these comparisons rigorous and precise. To make these abstract ideas clear, we will then work through several key examples, directly comparing familiar functions such as logarithms, polynomials, and exponentials to see how they stack up against one another. Finally, we will learn a powerful and widely used system called order notation, specifically the concepts of little o and big O, which provides a standard language for describing these important relationships. This framework is essential in many fields, especially for analyzing algorithm efficiency in computer science. To begin, I want to explore the idea of relative growth rates, which is all about comparing how quickly different functions increase as x approaches infinity. On one end of the spectrum, we have exponential functions like e to the power of x. These functions grow astonishingly fast, eventually outpacing any power function you can imagine. For example, the function e to the power of x will ultimately grow larger than x to the power of 1 million. Even though that power seems enormous. On the other extreme are logarithmic functions, like the natural log of x, which grow incredibly slowly. In fact, they grow slower than any positive power of x. To give you a sense of this, even a function that grows as slowly as x to the power of the quantity 1 over 1 million will eventually overtake the natural log of x. The key takeaway is that a clear hierarchy exists, where exponential functions always dominate power functions, which in turn always dominate logarithmic functions for large values of x. To build a strong intuition for relative growth, it is helpful to see these functions on a graph. Here we are comparing three familiar functions: the exponential e to the x, another exponential 2 to the x, and the polynomial x squared. Notice that for small values of x, say between 1 and 4, the parabola for x squared is actually the highest curve, which might seem counterintuitive. However, this initial behavior is not what matters as x becomes very large. As we follow the graphs to the right, you can see the two exponential functions quickly overtake the polynomial and begin climbing with astonishing steepness. By the time x reaches just 6, the exponential curves are already far above the parabola, illustrating a completely different scale of growth. The essential takeaway is that exponential functions grow fundamentally faster than polynomial functions as x approaches infinity. To make our intuitive comparisons of functions rigorous, we can define their relative growth rates using limits. We say a function f grows faster than a function g if the limit of their ratio, f of x over g of x, equals infinity as x becomes very large. This means g becomes negligible compared to f. On the other hand, if the limit of that same ratio is a finite, positive number, we say that f and g grow at the same rate. For example, the function 2x and the function x grow at the same rate because the limit of their ratio is simply 2. Do not confuse this technical meaning of growing faster with one function just being a constant multiple of another. The essential idea to remember is that the limit of the ratio of two functions is the ultimate test of their comparative growth. Let us apply our definitions to see how we can compare the growth rates of some familiar functions by taking the limit of their ratio as x approaches infinity. In our first example, we compare the exponential function e to the power of x with the polynomial x squared. Setting up the limit gives us an indeterminate form of infinity over infinity, which is a perfect time to use L'Hopital's rule. After applying the rule once, we get e to the x over 2 times x, which is still indeterminate. Applying the rule a second time gives us e to the x over 2, which clearly goes to infinity. Since the limit is infinity, we conclude that e to the power of x grows faster than x squared. The other two examples show a similar pattern. 3 to the power of x outpaces 2 to the power of x, and x squared easily outgrows the natural log of x. The main takeaway is that if the limit of the ratio is infinity, the function in the numerator is the one that grows faster. Now let us explore two more important growth comparisons, this time involving logarithmic functions. First, we will see that the natural log of x grows slower than any root function, x to the power of 1 over n. When we take the limit of their ratio as x approaches infinity and apply L'Hopital's rule, the expression simplifies to n over x to the power of 1 over n, which clearly goes to 0. This means that even a very slow-growing root function, like the millionth root of x, will eventually grow larger than the natural log. Second, we find that all logarithmic functions, regardless of their base, grow at the same rate. By using the change of base formula, the limit of the ratio of log base a of x to log base b of x simplifies to the constant value of the natural log of b over the natural log of a. Remember, this is unlike exponential functions, where different bases lead to different growth rates. The key idea is that all logarithms belong to the same family of slow growth. Sometimes, comparing two complex functions directly is difficult, so it is helpful to use a simpler, intermediate function as a common benchmark. This method relies on a property called transitivity, which states that if a function f grows at the same rate as g, and g grows at the same rate as h, then f must also grow at the same rate as h. For our example, let us show that the square root of the quantity 2x squared plus 5 and the quantity 2 times the square root of x minus 1, all squared, grow at the same rate. We can do this by comparing both of them to the simple function g of x equals x. The limit of the first function divided by x is 1, and the limit of the second function divided by x is 4. Since both limits are finite and positive numbers, both of our original functions grow at the same rate as x. Therefore, by transitivity, they must grow at the same rate as each other. Now we can formalize the idea of one function growing much slower than another using what we call little o notation. We say a function f is of smaller order than a function g if the limit of their ratio, which is f of x divided by g of x, equals 0 as x approaches infinity. For this limit to be 0, the denominator, g of x, must grow overwhelmingly faster than the numerator, f of x, essentially dwarfing it for large x values. For example, the natural log of x is little o of x because the limit of the fraction, the natural log of x over x, is 0. This confirms that the simple linear function x grows far more rapidly than the logarithmic function. So, when you see the expression f equals little o of g, remember it is a precise way of stating that f becomes insignificant compared to g for large enough values of x. A slightly looser way to compare growth rates is with big O notation, which tells us when one function grows no faster than another. We say a function f is big O of g, written as f equals O of g, if the ratio of f of x over g of x remains less than or equal to some positive constant for all sufficiently large values of x. For instance, the quantity x plus sine of x is big O of x because their ratio will always be less than or equal to 2. This is different from little o, where the limit of the ratio must be 0. This also means that if a function f is little o of g, it is automatically big O of g as well. Likewise, if two functions grow at the same rate, then each one is big O of the other. Essentially, you can think of big O as providing an upper bound on a function's growth rate. Let us apply our understanding of growth rates to the practical problem of searching for an item in a list. The most straightforward method is a sequential search, where you simply check each item one by one. In the worst case, For a list of size n, this takes n steps, giving it a complexity we call big O of n. However, if the list is already sorted, we can use a much faster method called a binary search. This approach repeatedly divides the search area in half, requiring a number of steps that grows logarithmically, which we describe as big O of log base 2 of n. To feel the impact of this difference, consider a list of 26,000 items. The sequential search might take all 26,000 steps, but a binary search is guaranteed to finish in 15 steps or fewer. For large problems, this shows that your choice of algorithm has an enormous effect on performance. Let us recap the essential tools for comparing how functions grow as x approaches infinity. The fundamental technique is to analyze the limit of their ratio, which reveals a clear hierarchy of growth rates. We established that exponential functions grow faster than any polynomial, which in turn grow faster than logarithmic functions. To formalize this, we introduced two notations. Little o, written f equals O of g, means that f grows strictly slower than g, because the limit of their ratio is 0. Big O, written f equals O of g, provides an upper bound, meaning f grows no faster than a constant multiple of g. We saw the practical power of this in computer science, where a slow sequential search is an O of n algorithm, while a fast binary search is an O of log n algorithm. In short, these notations give us a precise way to classify and compare the long-term behavior of functions. To finish, let us apply these ideas to a couple of review questions that test our understanding of relative growth rates. The first question compares two algorithms, one with a time complexity of big O of n, and another with big O of log base 2 of n. To determine which is more efficient, you need to recall which function, n, or the logarithm of n, grows more slowly for very large inputs, because a slower growth rate corresponds to a more efficient process. The second question asks you to verify two statements using our formal definitions. For part A, you will check if x plus the natural log of x grows at the same rate as x by evaluating the limit of their ratio. For part B, you will determine if e to the power of 2x is big O of e to the power of x by checking if their ratio remains bounded as x approaches infinity. Answering these correctly confirms that you can use the formal definitions to compare how different functions grow.